For 4,000 years, the survival of humanity depended on a single desperate search. How do you turn deadly mud into life-saving clear water? Every civilization that flourished did so because it solved this problem, and every civilization that failed to solve it was destroyed by the water it could not clean. Cholera, typhoid, dysentery. The waterborne diseases that killed more people than all the wars in human history combined were not defeated by medicine. They were defeated by engineering. The sand filters, the charcoal layers, the boiling pots, the chlorination systems, and ultimately the polyamide membranes that filter water at the molecular scale. Each one a harder-won answer to the same question that the first human being to drink from a contaminated river was asking. In this documentary, we trace 4,000 years of water purification engineering, from crushed seeds and sand layers in ancient Mesopotamia to the reverse osmosis systems of 2026 that are the only technology standing between a growing global population and a freshwater crisis that has no other solution. The engineering of clean water is the engineering of human survival, and in 2026, we need it more than ever. Did you know that modern human survival depends on a molecular battlefield just nanometers wide? Every time you drink tap water in a modern city, that water has passed through a filtration system whose most critical element, the membrane, is a polymer film so thin that it operates at the boundary between chemistry and physics, allowing water molecules to pass while blocking ions, pathogens, and dissolved solids at the atomic scale. The engineering required to manufacture a membrane with pores measured in angstroms, maintain it in continuous operation under high pressure for years without failure, and scale it to purify billions of liters per day is among the most demanding in the modern world. In this documentary, we trace the engineering journey from basic sand filtration to the complex membrane technology securing humanity's future, showing how 4,000 years of incremental innovation in the physics and chemistry of water purification produced the most important engineering system on Earth. From the Sushruta Samhita's boiling prescriptions to the graphene membranes of 2026, this is the story of how we learned to control water at the molecular scale. Imagine a world where every drop of water could kill you. For most of human history, that was not imagination, it was reality. The rivers and wells that supplied ancient cities were also the sewers that drained them. The water that kept you alive one day could kill you with cholera the next. The engineering challenge of water purification is therefore not an environmental luxury. It is the most fundamental engineering requirement in human history, the difference between civilization and extinction. 4,000 years of that engineering. From primitive fire boiling through the London cholera outbreak that proved filtration saves lives, to the reverse osmosis membranes that now desalinate seawater for hundreds of millions of people, is the story we are telling today. And in 2026, with global freshwater reserves under pressure from climate change and population growth simultaneously, the engineering of clean water has never mattered more. This is the incredible story of how we took control of water, and why losing that control is not an option. The first water purification engineers did not know what they were removing from the water. They knew only that certain treatments made water that had made people sick into water that did not, and they transmitted that knowledge across generations without any understanding of the microscopic organisms responsible for waterborne disease. The earliest documented water treatment prescriptions appear in the Sushruta Samhita, an ancient Indian medical text dated approximately 600 BC, but encoding knowledge considerably older, which recommends boiling water, exposing it to sunlight, and filtering it through sand and gravel before drinking. The recommendations are empirically correct. Boiling kills pathogens through thermal denaturation of their proteins. Sunlight exposure exploits ultraviolet radiation to damage the DNA of microorganisms. Sand and gravel filtration removes suspended particles and some microorganisms through physical straining and adhesion to the filter medium. None of these mechanisms was understood in 600 BC. The understanding was observational. Water treated in these ways caused fewer deaths than water that was not, and the engineering was a direct response to that observation. The Egyptians used alum, aluminum sulfate, to clarify turbid Nile water as early as 1500 BC. Alum acts as a coagulant. It dissolves in water and reacts with the dissolved minerals to form a gelatinous aluminum hydroxide precipitate that attracts and captures fine, suspended particles, forming larger aggregates, flocks, that settle out of the water column. The clarified water above the settled flock was decanted for use. The mechanism was not understood, but the effect was reliable and reproducible, and alum coagulation remains one of the most widely used water treatment processes in the world today. Crushed seeds, particularly the seeds of Moringa oleifera, a tree native to the Indian subcontinent, were used as natural coagulants in multiple ancient cultures. The seed contains a protein that, when dissolved in water, carries a positive charge that attracts and neutralizes the negatively charged particles, typically responsible for water turbidity. The resulting aggregates settle out, clarifying the water. The Moringa seed coagulant is still used in developing world water treatment applications. Today, a 4,000-year-old technology with a molecular mechanism that was understood only in the 20th century. Gravity-driven sand filtration. Passing water through a bed of clean sand removes suspended particles by physical straining at the sand grain, surfaces and by the biological activity of the microbial community that develops in the upper layers of the sandbed over time. The slow sand filter, allowing water to percolate slowly through a deep sandbed, is still used in municipal water treatment globally, 2,000 years after its empirical development. The Romans recognized the relationship between water quality and public health without understanding the microbiology. Their aqueduct systems were engineered to exclude surface contamination by carrying the water in enclosed conduits, and their settling tanks and distribution cisterns were designed to minimize the residence time of the water in contact with potentially contaminated surfaces. The first patented water filter appeared in England in 1791, a device using layers of sponge, charcoal, and sand to treat drinking water. The patent was empirical. The inventor knew the device worked but could not explain why. Activated charcoal, which would later be understood to remove dissolved organic compounds and some pathogens through adsorption onto its enormous internal surface area, was already recognized as an effective water treatment medium through centuries of observation. The connection between contaminated water and epidemic disease was demonstrated conclusively and spectacularly by John Snow's investigation of the 1854 Broad Street cholera outbreak in London. Snow, a physician rather than an engineer, mapped the distribution of cholera cases in the Soho district of London and identified a single water pump as the source. When the pump handle was removed, the outbreak ended. Snow's work did not immediately establish the microbial theory of disease that would require Pasteur and Koch, but it established beyond reasonable doubt that cholera was waterborne and that controlling the water supply was the critical public health intervention. The engineering response was the large-scale slow sand filter, a technology that London's water companies had been using since the 1820s but whose adoption had been incomplete and inconsistent. Snow's demonstration that filtration through sand removed the cholera agent drove the systematic adoption of slow sand filtration across British water supplies in the following decades. The mechanism of slow sand filtration was not the physical straining of the sand grains alone. The biological layer that forms on the upper surface of the sandbed, Schmutzdecke, is a complex microbial community that degrades organic matter, consumes pathogens, and transforms the physical filter into a biological treatment system. The engineered slow sand filter is not just a mechanical device, it is a managed ecosystem, and its effectiveness depends as much on the biology of the Schmutzdecke as on the physical properties of the sand. Rapid sand filtration, using coagulation to aggregate fine particles before they enter a sand filter, allowing the filter to operate at much higher flow rates than slow sand filtration, was developed in the United States in the 1880s. The coagulation, flocculation, sedimentation, filtration sequence that James Kirkwood and Alan Hazen developed for the Poughkeepsie water supply in 1872 is the basis of conventional surface water treatment plants still operating globally in 2026. Chlorination, the addition of chlorine compounds to disinfect treated water, was first applied systematically to a public water supply in Jersey City, New Jersey, in 1908. The reduction in typhoid fever mortality in the following years was so dramatic that chlorination was rapidly adopted across American and European water systems. The combination of filtration and chlorination, physical removal of suspended material followed by chemical killing of remaining pathogens, became the standard of municipal water treatment and remains so today. The development of synthetic polymer chemistry in the mid-20th century opened a completely new approach to water purification, membranes that could separate dissolved substances from water at the molecular scale, without any biological component and without the residence time constraints of biological processes. The first practical reverse osmosis membrane was developed by Sidney Loeb and Srinivasa Soraran at UCLA in 1960. Their cellulose acetate membrane had an asymmetric structure, a thin, dense skin supported on a porous substructure that allowed water molecules to pass while rejecting dissolved salts. The membrane worked by exploiting the thermodynamic principle of osmosis in reverse. Natural osmosis drives water from a dilute solution through a semipermeable membrane toward a concentrated solution. Reverse osmosis applies pressure greater than the osmotic pressure to the concentrated side, forcing water molecules through the membrane against the osmotic gradient, leaving the dissolved salts behind. The osmotic pressure of seawater is approximately 27 bar. To achieve reverse osmosis desalination of seawater, the applied pressure must exceed this value, typically 55 to 70 bar in practice. The energy required to generate and maintain this pressure is the dominant operating cost of reverse osmosis desalination and the primary engineering challenge of the technology. The thin-film composite polyamide membrane, developed in the 1970s, replaced cellulose acetate as the material of choice for reverse osmosis. A polyamide membrane consists of a cross-linked aromatic polyamide rejection layer, typically 50 to 200 nanometers thick, supported on a polysulfone microporous membrane, which is in turn supported on a polyester fabric. The polyamide layer is the functional element. Its cross-linked polymer structure creates a network of molecular scale pathways that water molecules can navigate but that are too small and too chemically inhospitable for hydrated ions, organic molecules, and microorganisms. Cross-flow filtration. pumping the feed water tangentially across the membrane surface rather than perpendicular to it, solved the fouling problem that had made early membrane systems impractical for long-term operation. In conventional dead-end filtration, rejected particles accumulate on the membrane surface and progressively reduce permeability. In cross-flow filtration, the tangential flow continuously sweeps rejected material away from the surface, maintaining permeability and allowing continuous operation without frequent backwashing. The spiral-wound membrane module, a configuration in which flat membrane sheets are wound around a central permeate collection tube, creating a high surface area in a compact cylindrical form, became the standard commercial configuration for reverse osmosis systems in the 1970s and remains so today. The Sorek desalination plant in Israel, operational since 2013 and expanded to produce 624,000 cubic meters of freshwater per day, is the archetype of the modern large-scale reverse osmosis desalination facility. It draws seawater from the Mediterranean, pre-treats it through ultrafiltration membranes to remove suspended solids and biofouling organisms, pressurizes it to 70 bar through high-pressure pumps, forces it through banks of spiral-wound polyamide modules, recovers the pressure energy from the concentrated brine stream through pressure exchangers, and delivers treated water meeting World Health Organization standards to the Israeli national water grid. The pressure exchanger, a device that transfers the hydraulic energy of the high-pressure brine stream directly to the incoming feed water, recovers approximately 95% of the energy in the reject stream that would otherwise be wasted. This single innovation reduced the specific energy consumption of seawater reverse osmosis desalination from approximately 10 kilowatt-hours per cubic meter in the 1980s to approximately 3 kilowatt-hours per cubic meter in 2026. A reduction that transformed the economics of desalination from an expensive emergency measure to a cost-competitive water supply option for water-stressed coastal regions. The engineering challenge of osmotic pressure management has driven the development of increasingly sophisticated membrane chemistry. The polyamide rejection layer of a modern membrane is engineered at the molecular scale. The degree of cross-linking, the density of charged groups, and the hydrophilicity of the surface all optimized to maximize water permeability while maintaining ion rejection above 99.7%. A membrane that rejects 99.7% of salt passes 0.3%, producing water with a salt concentration of approximately 150 parts per million, from seawater at 35,000 parts per million. The scale shift from industrial to portable reverse osmosis systems has been as significant as any advance in the technology. A 2026 expedition-grade portable RO unit, battery-powered, capable of desalinating seawater or purifying highly contaminated surface water, small enough to carry in a backpack, delivers the same molecular scale filtration as a plant, costing hundreds of millions of dollars, at a flow rate appropriate for individual survival rather than municipal supply. The underlying membrane physics is identical, only the scale, the pressure source, and the energy supply differ. The same technology that secures the water supply of a coastal megacity is folded into a device that a solo sailor uses to survive an unplanned ocean crossing. The global freshwater crisis of 2026 is not a future scenario. It is the present reality for approximately 2 billion people who lack access to safe drinking water and a near-term threat to the agricultural systems that feed the remaining 6 billion. Aquifer depletion, glacial retreat, and the redistribution of precipitation driven by climate change are simultaneously reducing the quantity of accessible freshwater in the regions that most need it. The engineering response, desalination, water recycling, and atmospheric water harvesting, depends entirely on membrane technology for its implementation. Graphene oxide membranes represent the most significant potential advance in membrane engineering since the development of the polyamide thin film composite, a single atom-thick sheet of carbon atoms arranged in a hexagonal lattice. Graphene has mechanical properties that exceed those of any conventional polymer membrane, while offering the possibility of atomic scale control over pore size and chemistry. Graphene oxide. Graphene functionalized with oxygen-containing groups that make it compatible with aqueous environments. Can be assembled into membranes with interlayer spacings of approximately 10 angstroms, large enough to allow water molecules to pass freely but small enough to exclude hydrated ions. The theoretical water permeability of a graphene oxide membrane is orders of magnitude greater than that of a polyamide membrane of equivalent ion rejection, potentially reducing the energy required for desalination by 90% if the manufacturing challenges of large-scale graphene membrane production can be solved. As of 2026, graphene oxide membranes are in advanced laboratory development and early commercial trial, with pilot installations operating in research facilities in Australia, Singapore, and the United States. The manufacturing scalability, producing defect-free graphene oxide membrane sheets at the areas required for commercial water treatment, remains the primary engineering challenge. AI-driven filtration management is transforming the operational efficiency of existing membrane systems. Machine learning algorithms trained on the fouling behavior of specific water sources can predict the onset of membrane fouling before it occurs, scheduling preventive cleaning cycles at the optimal moment, maximizing membrane life while minimizing the energy and chemical costs of cleaning. Self-healing membrane materials. Polymers engineered to reform their cross-linked structure when damaged by oxidizing agents or mechanical stress are in active development, with the goal of extending membrane replacement intervals from the current 3 to 7 years to indefinitely. Sustainable operation. The convergence of graphene membrane permeability, AI-optimized operation, and self-healing material chemistry represents the endpoint of 4,000 years of water purification engineering. A system that removes every contaminant from any water source at any scale, with minimal energy input and no consumable components. 4,000 years ago, a physician in ancient India prescribed boiling and sand filtration because the water was killing people. In 2026, a polyamide spiral-wound module in a coastal desalination plant is keeping people alive by the same fundamental principle: remove what should not be. In the water, deliver what should. The contaminants have changed. The engineering has become incomparably more sophisticated. The imperative has not changed at all.